Okay, so average rate of change. So we know like the word rate of change. What are you doing now? Oh, okay. Real smooth. Real smooth. So rate of change, when you see rate of change, like in your head, in the context of math, immediately you might think slope. And tangent lines, what's it mean? Like in geometry, when you learned about tangent line, what did it mean? Gabe?
It's a line that's touching a point on the circle.
Yeah, so it's a line that's only touching 1 point at a circle. What do you call a line that touches 2 points on a circle? Secant. It's a secant line. A secant line touches a circle twice. A tangent line touches it once. Okay, so this is an example of a secant. A secant touches a circle at 2 points. Versus a tangent only, oh my god, that was bad. Hold on, go back. Okay, we'll try again. Touches exactly at 1 point. It's a nice straight line. A tangent line is going to be directly perpendicular to, like, if it's on a circle, it's directly perpendicular to the radius that touches at that point, that goes to the center, but that, who cares about that? Here, what we really want to know, what I'm trying to give you a taste of, is guess what? 2.4 is all about slope, and we're going to be talking about tangent lines, so we're going to be talking about slopes, instantaneous slopes at a single point. Right? So a tangent line to maybe I have a crazy looking graph. So I have this crazy looking graph. Oh, that's not. Dang it. That's not so crazy. Nope, it's not at all. So I have like a graph that maybe looks like that or something, right? So I want to know, what is the slope? What's the instantaneous rate of change at that 1 point? I could make a tangent line and wait, the tangent line is straight, so I could calculate the slope. And then I could see what the change is at that point. And then I go somewhere else. Maybe right here. Ooh, that's a nice steep slope. So I take the tangent right there. I could see how I'm changing at that instant of time. Okay, a little, it's more or less. We went over this last year. So average rate of change, the average rate of change is you take where you end minus where you begin over the total interval. Okay, or literally it's the slope equation, y2 minus y1. Over x2 minus x1. So, you know, let's say I'm driving to Vegas. So I start at LA. I go to Vegas. I don't know, it was 241 miles. I have no idea. It just sometimes takes 5 hours, sometimes takes, 8 because Coachella traffic. That was very specific. That was April 2019. 8 hours. Okay, so if I don't know my average rate of change, I know that I start here, I end in Vegas, cool, 200, let's make it 240 miles. Okay, so I know that in my little example, I end at 240 miles, I start at my 0 mile, I end at 5 hours, and then I start at my 0 hour, right? I start my stopwatch. So this means that my average was 48 miles per hour. Was I going that fast? Yeah, for instance of time, but I'm stuck in LA traffic, no, I was going like 20. And then there's points when I'm driving where I'm going like way faster. But this is the average. At times I could be hitting this, but this is the average. So I'm trying to make it clear the difference between this equation that we're going to be using and the one at the end of 2.4, which is more instantaneous at that single instant. Because people are crazy when they're driving on that 15 going between Nevada. They go like 100 miles an hour. So,
Fast on the 118 too.
People go fast on Van Owen.
I'm scared of the 118. I don't like it.
Well, until there was that one time I was driving and I got stuck for 3 hours because there was a bad accident and they just shut the whole freeway down and we're just chilling there. In the middle of the desert. Middle of the desert. So hot. Okay.
The faster you go, the more breeze you get when you open the window.
Yeah, but okay. All right. So my point of bringing this up is I want you to understand the average rate of change isn't necessarily, you're not going your average the whole time, right? It's just, okay, if I'm just looking at the total distance I traveled over the total time it took, this would be the average amount versus the instantaneous is like, okay, well, how about now? How fast am I going? It's a speedometer. At every moment you look down, you're getting your instantaneous rate of change, how fast you're going at that time. Okay, so this equation, f of t2 minus f of t1 over t2 minus t1, wait, that's like 2.1. Remember our first lesson of this? We talked about this. In the chapter, in section 2.1 of the chapter, we talked about this already. Okay, I'll just scroll up. Yeah. Whoa. Okay. Wait. Oh, look, average speed. Oh my gosh. This is exactly what we're doing right now. Average speed, f of t2 minus f of t1 over t2 minus t1 over the time interval from time 1 to time 2. So let's say I was interested in looking at my average speed between here and Bakersfield? Barstow.
What?
Yeah, what? I said I am Barstow.
What is that?
That's a town?
You don't know Barstow?
Barstow's a town.
I don't know where
It's like it's the halfway point. I'm just okay. I've been to between here and Vegas.
Oh, I never.
I've gone to San Francisco once. I'm more like I've been to Vegas a couple more times. So I'm more no. Okay, you know what? I'm not from LA. I'm trying to think of things that are more like relatable so you can like see it in life. Okay, whatever.
Where are you from?
Nebraska. I'm from Nebraska. Shh. Okay, so I'm explaining why we have this time interval from T1 to T2. Why would I say this if we always start at 0? Well, we don't. We don't always start at 0. Let's say I'm interested in my average rate of change from here to Barstow versus Barstow to Vegas, right? So wait, when I'm going Barstow to Vegas, I'm not starting at time 0 because I started in LA. So that would be like, from hour, 3 to 4. Versus my first interval, which was from 0 to 3, right? So this T1 and T2, the T1 doesn't necessarily have to be 0. It just depends where you're starting. Okay. Anything else I want to say about this? No, I already covered the function, the difference in function. Okay, cool. So we can go over the first example. Find the average rate of change. So this is your key. When it says average, or when you're trying to find a slopey slope, this is when you're going to use it. All right, over the interval, so f of x equals square root of 2x plus 1 from 0 to 4. So this tells you our interval. So here we are actually starting at 0. So I want f of 4 minus f of 0 over 4 minus 0. So if I plug in 4 times 2 is 8 plus 1 is 9, so square root 9 minus... Okay, do you want me to plug in? So I'll show you. So here, 2 times 4 plus 1 minus square root of 2 times 0 plus 1 over 4 minus 0. So I plugged in for the function values. Square root 9 minus square root of 1 all over 4. So it says 3 minus 1 all over 4. So that's just 2 fourths, or aka 1/2. That would be the average rate of change. So it's like I took a point here and a point here and I drew a straight line. This would be the slope. This is the slope of my line. Remember what type of line is this? It intersects my line 2 points. It's a secant, exactly. So average rate is pretty much always going to be your secant line. Your tangent line comes into play when we start talking about, taking the limit as h approaches 0 and taking a tangent at one point, the instantaneous, that would be more your tangent. Okay, cool. So average rate is like your secant. You're literally drawing a point from where you start and where you end, and it's a slope in between. So I'm sure at one point, it's probably going to be matching the slope here. But, at first, if you look at this, at first, the slope is much steeper, and then as we get later, it's much more shallow. So later, you'll learn this is Rolle's theorem of calculus, but it's fine. We aren't there yet. Okay, cool. Let's take the next one. So f of x equals 2 plus sine t. I'm going from 0 to pi. So I'm going from here to here. So I'm only interested in these points. Ooh, so if I would draw a line here, do we know what our answer should be? So it's a secant, but what is the slope here? 0. Okay, you know what? Let's double check. Let's do it algebraically. Let's double check that this is correct. Because we won't always have a graph, and it might not always be this easy. But just going through, we know what the answer should be. Cool to double check. So I'm going to be taking f of my secant, so f of pi minus f of 0 divided by pi minus 0. So we'll plug in. So I have 2 plus sine pi minus 2 plus sine of 0. Trying to make sure it's on the screencast. Okay. All over pi minus 0. What is sine of pi? 0. What's the y value of pi? 0. What's the y value of 0? 0. 0. Cosine of 0 is 1. Cosine of pi is negative 1.
What is pi minus 0?
Pi. So I have 2 minus 2 over pi. 0 over pi. What's 0 divided by any number? 0. Oh, cool. So this is exactly what we got in the first place. Aha! We knew what the answer should be. We double checked. Okay. I want to make sure I'm not going too fast. Do we have questions over this? So when you're thinking average rate of change, you're thinking the slope of the secant line connecting your initial and final points. Because I know that last year I tried making this very clear. People still missed it. So I'm, over beating into your head. Secant is the average, right? Literally, this is the slope of your secant line. Okay. Example 2. The figure below shows the growth of a fruit fly population in a controlled experiment. Compute the average change and slope of the secant line PQ. Interesting. Okay, so the average rate of change is delta P over delta T. So change in y over change of x. So this would be 45. Oh, wait. So 340 minus 150 over 45 minus 23. Because they gave us the 2 points we're interested in. Pretty cool. So let's see, this turns into 190 over 22. 190 over 22, yeah. So that's roughly going to be about 8.6. It's about 8.6 flies per day. I didn't do this in my head. I went through the notes before to try to think of what would be confusing. Sometimes people are unreliable calculators when I'm like, all right, do it. No, let's go. Come on. Oh my gosh. Okay. So that is the average rate of change between these 2 points. What is the slope of the secant?
8.6.
Aha! Yes. Once again, beating it into your brains that the average rate of change is the slope of the secant line. Oh my god. Oh my gosh.
But
Oh my gosh.
that's only the
Same.
line for a certain segment of the experiment. That's only during the period from 20 days or from 25 days until 46 days.
Yep.
You're not counting from 0 to 50.
Exactly.
Does that make sense?
So the average rate of change, we always have to have initial point and final point, right? And so when you connect those 2 points with a secant line, the slope of the secant is going to be the same as the average rate of change between those 2 points. Because your secant line always goes through the 2 points you chose.
But it's not, is it asking for the rate of change between those 2 points?
Yeah,
or
it is.
the entire thing?
It wanted between those 2 points.
Oh, okay.
Yeah. Yep. All right. So we can always think of average rate of change as the slope of the secant line. I feel like I've said that 15 times today. Okay, so now let's talk about tangent to a curve. Are you okay? Sugar crash.
Yeah.
Tangent to a curve. Okay. So the rate at which the value of a function is changing with respect to x at any particular value, x equals a to be the slope of the tangent of the curve, blah, blah, blah. Okay, so what the heck does this even mean? So we had a graph up here, and we found the average rate of change between where we start, the 23rd day and the 45th. But what if I wanted to know, well, on the 23rd day, how fast was it changing? I don't really care, from the 23rd to the end, but on that specific day, how is it changing?
150 over 23.
Well, that would be the average from the start to the end. That would be this secant line. Yeah, because then your initial point 0. Okay, so if I want the slope at that one point, I would have to draw a tangent line Oh, this is okay. Let's try this again. I was so close. I was not close at all. Oh, got it. Got him. Do you see it?
Yeah.
Okay. You don't understand how hard this is. I'll change the color so you see it better. Okay. Boom. Okay. So it's only touching the graph at that one point. Well, okay. Ignore this part right here. Okay, ignore that part because that's different. And the graph is like coming back up. But it's only touching the graph right here. Right? So around it, it's very close. But as we zoom in further and further, it's only going to be touching at this one point. So we're only looking at this little section, only touching right there. So with a tangent, right, tangent to the graph, the tangent line only touches it at one point where secant crosses it twice. The tangent would give us a better estimation of what the rate of change is there. How does the slope of this tangent line in green compare to the black one, which is the secant? Okay, so we see the touching. What about number-wise? Number-wise, how are they different? Steeper, right? So we see that if I found the tangent, if I found the instantaneous rate of change at point P, it would be higher than what the secant, higher than the average would be, because it was a steeper slope at that point. So the tangent to the curve, it gives me, so this tangent, what the thing below is saying is if I want the rate of change at this single value, at this one point, not overall, I'm driving and I'm like, oh my God, I see a cop. How fast am I going right now? I can't get out of a ticket saying, oh, I was only averaging 48 miles an hour. No, I was going 90. Like, I can't do that, right? Instantaneous. How fast are you going at that one point? You would have to draw a tangent at that point. So literally the tangent line is only touching at the point we're interested in. And then we find the slope of that tangent line. Okay, that is like in, the common tongue basic English of what this stuff right here is saying. If you want the rate of change at a specific single value, then you have to make a tangent to the curve at that one point. Cool. So then how do we define the tangent line at an arbitrary point P on the curve and find its slope from the formula when our usual definition of slope requires 2 points? Remember, we're trying to find slope with a tangent, but I only have 1 point on my line. So how do I have a second one? There's this beautiful, brilliant man named Pierre Fermat. All right, so in 1629, yes. Yeah, and I think we'll talk more about him in this year. If not, if you could keep taking math, you'll hear more about him. Brilliant man, most likely European, white man. Cool. Found a solution in 1629 that we still use today. So that's crazy. That was a long time ago. So first, we start with the slope of a secant through P and Q. And then we find the limiting value of the secant slope and a point Q nearby. And then we define the slope at this number, blah, blah, blah. Okay, so what's really happening? So I pick 2 points, right? So I have the one I'm interested in, and I have this random second one. And then what happens as I keep moving my second point closer and closer and closer? Remember we did F plus H, right? Our H is the gap. H is the gap between my first number and my second. We did this. Okay. So I'm just explaining again. So as the gap between my first number and second number gets smaller and smaller, my second point gets closer and closer until I'm really, really close. And so the secant line is a good approximation for what the tangent line would be. Okay. Cool. Let me see. I think this is what the image is. I think that's what I chose for the topic for this chapter. Did you guys see how I have a GIF for the topic?
Yeah.
On my jag? Yeah. So I am pretty sure that's what I chose. All right, let's do this. Thanks. Well, I had to have it for, LinkedIn and stuff. Why is it not going? Okay, here we go. Oh, no, that was just a.
All Pierre discovered.
No, this is not it. That was not it. I thought I did it, but I did not.
Pierre, step up your game.
That's not what he discovered. That was the definition of a limit. Okay. So as I pick points that are closer and closer, so notice that notice that, oops, that was wrong. So as I pick points that are closer and closer, the tangent line, the secant line gets closer and closer to the tangent. Pick here, it gets closer and closer to the tangent. So let me try that again with an actual line. So, oh, that's not an arrow, okay. So that line, this line, notice I'm getting closer and closer to the pink one, that's the actual tangent. No. Yeah. Yeah, this is what he discovered.
That's still pretty light.
Don't say lame, I'll be so sad.
That's still pretty light.
Oh,
okay.
I was changing the color so you can see it better. Okay, so if I pick my second point, as I shrink h as the distance between my first x and my second x, right, the 2 points I need to find slope, as the distance between them gets smaller and smaller, the graph of the secant line between my 2 points gets closer and closer as a good approximation for tangent. That's all this right here is saying. That's what it's saying. As we start with the slope through a secant point P and Q nearby on a curve, we find the limiting value of the secant slope as Q approaches P along the curve. Okay, aka, as we move these 2 points closer and closer together, guess what? Secant slope getting closer and closer to tangent slope. That's what it's saying. We define the slope of the curve P to be this number. Hey, guess what? As we get really, really close, it's pretty much the same thing. We say, you know what? That is the slope of the tangent. All right. I'm a translator. I should get paid for this. Like, go through the world and translate for technical things. I mean, I do get paid to teach you this, but okay. You know what I mean? Yeah. Yeah. Cash. Okay. Okay, so now that we've discussed it a lot, hopefully this looks a little familiar. If not, no worries. We're doing it again. Slope of a curve at a point. So this plus h is the distance between your first point and second point. And as we shrink the distance between these 2 points, my slope between them gets closer and closer to the tangent. So as h approaches 0, as the gap between them gets to 0, what is the actual slope? What is the slope of the tangent line? So this is slope of a curve point is the tangent slope. The slope of a curve at a point is this number. So this is slope at a specific point. Yes. Slope at a specific point. At a specific point. Find the slope of the parabola at the point. Oh, it doesn't say average. It says at this point. All right. Write the equation for the tangent to the parabola at this point. So we'll do this problem and then we'll just end for today. Okay. So then write an equation for the tangent to the parabola at this point. So at the x value. Okay. So first, let's write down. Let's see, we're finding tangent slope. Okay, so first, let's just write the equation out, what I had up above. So I know m, the slope of my tangent, is going to be, let's see, limit as h goes to 0, as the distance between my 2 points gets closer and closer, as the distance between them goes to 0. I have f of a plus h minus f of a all over h. So normally, I mean, before we've said f of x plus h minus f of x over h. So here we're just saying like a is my x value. A is my x value. All right, and we're looking at this point 2, 4. So that's not accurate. Let's try here. It's pretty close. Not perfect. One more time. Okay, cool. So that's really close, actually. You see how it only touches at this one point right here, the 2, 4. At this one point, I want to know what is the slope. So I'm trying to find at 2, 4. So I'm going to be plugging in 2 for my a value. So I have limit as h approaches 0 of f of 2 plus h minus f of 2 all over h. And remember, the equation we have is y equals x squared. So I will be first plugging in I'll be plugging in 2 plus h squared minus 2 squared all over h. This is me plugging it in to the function value. So you remember? Yeah?
Huh?
Wait, never mind.
I said I remember and it was horrible.
So then the A, what's the problem? Plus A, the X.
Yeah, sorry, a was the x value.
Is that always the case?
So then, and this the equation the book gives, it gives it in terms of a, so that's your x value. Okay, so we know.
Actually, was like, oh, this is familiar to this thing that we're learning, like last week, and I'm like, when are we gonna do that? I remember it was horrible. I'm like, now we're doing it.
Surprise. Okay, just a little aside. 2 plus h squared means 2 plus h times 2 plus h, so that's 4 plus 2h plus 2h plus h squared. Just make sure we remember how to FOIL. This is the one time I'll do it. It is not 4 plus h squared. You're forgetting about the O and the I of FOIL. You got to FOIL, not. All right, so whatever. Cool. So that goes away. Oh my gosh, I can cross out one of the h's.
4 plus H.
4 plus h, and as h goes to 0, it's 4. So this is the slope. M equals 4 is the slope, but that is not quite done because we have to find an equation for the tangent to the parabola at this point. Okay, so what equation would it be? So we have to find the equation of the tangent line. We found the slope, but we have to find the equation of the tangent line. But we have a point, right? It gave us a point, 2, 4.
Point slope.
And we have a slope. Oh my god. Point slope. Oh my gosh. You use point slope. Okay, so y minus 4 equals 4 times x minus 2. Beautiful. You can leave it this way, or if you're not happy, put it in slope intercept form.
M equals 4? How do you get that M equals 4?
That was.
Because H is
Okay, I'm gonna stop you.